Hi, I'm Fernando Pereira from UFMG, and today we shall see another important property of type systems. This property is called preservation. We state preservation as follows. If T is a term and has type big T, and there is another term T prime such that T evolves to T prime, then T prime also has type big T. In a sense, the property says that the types of terms are preserved whenever those terms take step. Let's prove preservation for our toy language with its simple type system. So let's assume that we have used T_true to show that T has type big T. In this case, T is the value true. Can we take a step? Well, not really. There is no rule that evolves the value true. In other words, if T is true, then the statement of the theorem cannot be fulfilled. In other words, the theorem is vacuously true for T equal to true. The same holds for T equal to false, or to T equal to 0, or to T equal to suc of a numeric value. In all these cases, there is no way to take a step, so we do not have to worry about these terms. Let's now look into a term that can take a step. If T1 then T2 else T3. In this case, we know that T1 has type bool and that T2 and T3 have a type big T, which is the same for both. There exist three rules that we can use to evaluate an if-then-else. They are if true, if false, and if. So if we have a term typed with rule if and we use if true to take a step, how can we show that the resulting term has type big T? If we use rule if true, then we know that T1 is the value true. In this case, the if-then-else evolves to T2, which has type big T, which is the type of the original if-then-else expression. In the same way, if we use the rule if false to evaluate the term, then we know that T1 is false and that the term evolves to T3, but T3 has type big T, that's in the premises. And we are done, for the resulting term T3 and the original if-then-else have the same type. Now, would you like to stop the video and think about how we can prove the theorem for if? In this case, we know that T1 takes a step. In other words, there exists a term T1 prime such that T1 goes to T1 prime. By induction, the type of T1 prime must be bool. For preservation holds up the derivation tree. In this case, we can use bool if to take a step. We can use if because the premise is true, that is, T1 evolves to T1 prime. So we know that T1 prime has type bool. We know that T2 has type big T and that T3 has type big T. We can reuse the rule if to type check the new if-then-else using T1 prime instead of T1. That's all a matter of plugging the right facts in the right places. So can you take a look into this figure? Just stop the video and try to figure out what it means. The red boxes mark facts that we know that are true from the premises of the theorem. For instance, if we assume that we have used if to take a step, then we know that T1 evolves to T1 prime. The blue box marks a fact that we learn by induction, and the green box marks the final fact that we want to show that if T1 prime then T2 else T3 has type big T. We can use the same approach of drawing the facts to prove the theorem for the other typing and evaluation rules. For instance, would you like to stop the video and then try to show that the theorem is true when we use T_suc and E_suc? I leave the example of the if-then-else to you. Here you have the proof. Again, the red boxes mark the facts that we know that are true due to the premises. Blue indicates that we learn from induction, and green is what we want to prove. In other words, we want to find a type for suc T1 prime, and the arrows show how we plug facts to derive this type. You can apply similar principles to show that a theorem is true when the typing role is T-pred. But in this case, there are three possible ways to take a step. If we use E-pred 0, the proof is simple, because we know that T prime is 0 and the type of 0 is always net, which is the type of pred 0. Now, would you like to draw the proof of the theorem for E-pred suc? Here's the pictorial proof. No induction is necessary in this case. We know that NV1 is net, because suc NV1 is net. The only case that remains is E-pred. In this case, we will need to use induction. Perhaps you would like to draw the proof? Here's the proof. Notice that we are using the red boxes and arrows to plug the facts in the theorem inductively, and we conclude that T1 prime is net. We can use this fact to conclude that pred T1 prime is also net. We have a few more cases to demonstrate, but they are all similar. For instance, if we use T is 0 to type the term T, then we know that the term has the form is 0 T1. In this case, there are three ways to evaluate the term. The first two are E is 0, 0, and the second is E is 0 suc. In both cases, we know that T prime is a value. In one case, it's true, and in the other, it is false. In both cases, they have Boolean types by definition. Would you like now to draw the proof for E is 0? Here's the drawing of the proof. We are simply plugging the facts that we know from the premises in the theorem, again, to derive that T1 prime is net by induction. From this new fact, we can use T is 0 to derive that E0 T1 prime is bool. The property of preservation is also called subject reduction. If we say that T has type big T, then T is the subject. I mean, the term T is the subject of the sentence. When we take a step, we are reducing the size of T, so we are reducing the size of the subject. But notice that preservation holds only in one direction. If we expand a term, then preservation is not guaranteed to hold. For instance, if false then true else 0 has no type. But this term evaluates to 0, which has a type. And with this final observation, we conclude this class on type systems. The literature about types is huge. I've listed a few papers here, but again, the most definitive book on the subject is Peirce's book, Types and Programming Languages.